Here is all the work and the answers to check all of that. They give us the number of acres equation, and then the first part says find the average number of acres. So that is your average value formula. So 1 over b minus a times the integral from a to b. So use your average value formula, math 9 that thing, get the total number of acres. Practice that in your graphing calculator. Part B says find the time when the instantaneous rate of change, which is the derivative, is equal to the average rate of change, which is the slope formula, and over that interval. So I did my derivative, set it equal to the slope formula, plug the numbers into the calculator a little bit there. There's our derivative. And then whenever you have a difficult equation, move everything to one side, graph this in the graphing calculator, set it equal to 0, and then do the viewing window from the x-min and the x-max from 0 to 4, and let it calculate that 0 for you. Make sure you can do that correctly in the graphing calculator. Please practice all the graphing calculator stuff on this particular problem there. And then let me know if you have any questions. Letter C. Seems like it's a little bit tricky, but it's a pretty easy problem. The key phrase here says, write a limit expression that describes the end behavior of the rate of change. So the end behavior, you know that means as you're going to infinity, negative infinity, stuff like that, the end behavior of a graph of the rate of change. The rate of change is the derivative. So, and it says write a limit expression. You need to show, you always got to show the setup for your integrals, show the setup for your calculations. You need to have the limit expression in there, and you show them what you're taking the limit of. So it's just a limit as t approaches infinity of that derivative. And when you plug in infinity, that's just a number over infinity, or a number over a million, a number over a billion. So that answer will approach 0 there. But make sure you show your setup with your limit notation and then your answer of 0. And then the last part, again, practice this stuff in the graphing calculator. They give us this a of t function, and they want to say, where does that obtain its maximum value over the closed interval? So that is an absolute extrema problem where you're going to make like an XY chart or a TA chart, and you're going to check the endpoints of your interval and any critical numbers. The critical numbers is where the derivative is equal to 0. So there's our original function we're trying to maximize. The derivative of c is c prime. The derivative of an integral is that inside function right there. So there's our derivative. I got to figure out where it's equal to 0. So I graphed the derivative minus that in the graphing calculator over the interval between 4 and 36, and then where it crossed the x-axis, it calculated it for me. That's where the graph crosses the x-axis there. So that's our critical number. And then you're trying to maximize the a of t, which is this. So you got to take these 3 numbers, plug them in for the t right there and for the t right there. Now, what you could do is you could graph the c of t you could graph this function in your graphing calculator and just use that trace button, or you can take each of those numbers and plug that in for the t right there. But there I kind of did those individually and kind of wrote those numbers down, and then you're going to do the math 9 of 4 to like 4, and then 4 to 36, and then 4 to that 11.42 number like I'm showing here. So please practice that stuff in the graphing calculator. That's your setup, taking the derivative, set it equal to 0. And that's your justification to verifying that that is the highest y value right there. And it says at what time does it occur? So that's your 11.442. Quilt.